What are we going to eat later on?
Oh, the oh my god burger.
Oh my god!
Thanks for watching, and by popular demand, today I will give you a very brief overview of the beautiful world of linear algebra. And I'm not gonna go through the details, it's basically a very non-technical overview if you want. And also it's a very broad field, so I've just selected a couple of topics. But of course I could just talk for hours about it. So what is linear algebra? It should be called linear geometry, because what we're gonna do, we want to study the geometric properties of solutions to linear equations. So what the hell do I mean by that? And let's maybe just go by steps or chapters. Namely, for example, let's study systems like that. So solve. You just solve by start to solve systems like in Algebra 2, something like that. 2x1, x1 plus 2x2 minus x3 equals to minus 1. 2x1 plus 2x2 plus x3 equals to 1. 3x1 plus 5x2 minus 2x3 equals to minus 1. So you start by, usually a course in linear algebra starts by solving basic systems like that, and you learn a technique that's very standard and that works every time, and it's called Gaussian elimination. It's based on Gauss, very popular guy, and but I will not show you how to solve this. Maybe if you request it, I can do it in another video, but again, just believe me, there is a systematic way of solving this, and just in case you're curious, in this case, the solution is x1 equals to 4, x2 equals to minus 3, and x3 equals to minus 1. So in this case, we have exactly one solution. And it turns out, and here's the interesting thing, such systems, they only have either one solution, no solutions, or infinitely many solutions. And I'll touch on that later, but there's never the case where you have two solutions of this system, which makes it very different from nonlinear cases. Here, and I forgot to say, it's linear because you have a constant times x2, a constant times x3. You don't have any squares or logarithms or trigonometric stuff involved. So it's really, really basic systems. So, and once you learned how to solve the system, the next step is really to figure out how to rewrite this in another, maybe cleaner way. It turns out you can rewrite this in what's called a matrix form, namely, the system is equivalent to AX equals to B, where A is the matrix of coefficients. Maybe let me elucidate here. Here the coefficients are 1, 2, minus 1, 2, 2, 1, 3, 5, minus 2. So, right now, it's just a square that gathers all the coefficients, and it's called a matrix. Yes, matrix. Okay. And X is just a vector of solutions. x1, x2, x3, and B is the vector minus 1, 1, minus 1. And those are called vectors. So, just like you learn in multivariable calculus, just stuff with a bunch of components. And it turns out, and this shows by definition of linear systems, that any linear system can be written in this way. So whenever you talk AX equals to B, it shows you're just talking systems. It's like talking trash, but it matters. Okay, that's one thing, and then for a little while what you do, so maybe in the next chapter, so maybe it's chapter 2 or step 2, you just basically study more of those matrices. You're like, what can we do to this matrix? Can we multiply them? Can we take 1 over A? And by the way, that would be useful because if 1 over A exists, then you can start with this equation, multiply both sides by 1 over A. So 1 over B. And remember, 1 over something times something, that's 1, provided that something is non-zero. So, and 1 times x is just 1. So you get x equals to A inverse B. So the cool thing is, if the matrix has an inverse, if you can define A inverse, then it gives us an automatic way of solving this equation. So it's a very nice theoretical aspect, but of course it turns out it's not always true. Like if A is a zero matrix, this would not hold, and so a bunch of chunk of time is not wasted, but is devoted on figuring out when this matrix A has an inverse. And so it was one thing, talking about AX equals to B. And now, even though we're interested in solving AX equals to B, it turns out there's a special case that's absolutely important, namely the case B equals to 0. So maybe the next step, I guess step 3, is to analyze or study AX equals to 0, where 0 is just a 0 vector. And for example, in the above example, the system would be x1 plus 2x2 minus x3 equals to 0, 2x1 plus 2x2 plus x3 equals to 0, and 3x1 plus 5x2 minus 3x3 equals to 0. So the same equation as above, except the right-hand side at all zeros. And the reason this, and by the way, if you solve this, in fact, you get that the only solution is x1 equals to 0, x2 equals to 0, x3 equals to 0, but it's not always the case. There could be non-zero solutions to this. And the reason this is so important is because there is the following theorem, following fact, that says, in fact, solutions of AX equals to B are not very different from the solutions of AX equals to 0. So, namely, the general solution of AX equals to B is always of the following form. Namely, x, again, the solution of AX equals to B, equals to x naught plus xp, where x naught is the general solution to AX equals to 0, so this equation we talked about, and xp is just a particular solution. Solution to AX equals to B. So this is really, really cool. What it says is, let's say you solve AX equals to 0. You find x, and you just find one solution to AX equals to B, then it turns out that you can actually find all the solutions. And by the way, if you've taken differential equations, there is a very analogous theorem that says if you want to solve a differential equation with an f term on the right-hand side, all you have to do is find a general solution but with 0 on the right-hand side, and just a particular solution with f on the right-hand side. And you can find that using undetermined coefficients and variation of parameters. That's why, usually linear algebra and differential equations, they're put in one course because there's this nice analogy between that. And let me just illustrate this for sake of definiteness. So for example, the general solution to, let's just consider this system, 2, 1, 1, 2, 3, 1, 1, 2, 1, 1, 1, 2, 4, 1, 2, 3, minus 9, minus 3, minus 5, 8. I took this from a textbook, I didn't make this up. Okay, x1, x2, x3, x4, 0, 0, 0. Let's say you solve this, again, that's ax equals to 0. Okay. Then, if you find the general solution, it turns out the solution is just a real number times the vector minus 2, 1, 1, 0, 0. Oh wait, no, maybe, sorry. x4, x5. Okay. Is a real number times the vector minus 2, 1, 1, 0, 0 plus another real number times 2, minus 1, 0, 2, 1. So remember this example is very useful. Ts in R. Okay. So let's say you find this and the general solution is this. And let's say, just out of the hat, you find that the particular solution of this thing, ax equals, let's say this thing, 17, 6, 8, 14 is xp equals to 3, 1, 0, 2, 0, then, as I said, you can solve ax equals to the general solution of this of ax equals to 17, 6, 8, 14 is just, so this solution 3, 1, 0, 2, 0 plus t minus 2, 1, 1, 0, 0 plus s 2, minus 1, 0, 2, 1. So the point is, all you have to do is add those two things together and you get the general solution of your equation. The point of this is, this equation is actually very, very important, where the 0 is on the right-hand side. And in fact, it's so important, the set of x that satisfy this, they're in the kernel of A. So not like Colonel Sanders, but as in, it's important, So, like, as if, the kernel of a popcorn is very important related to the popcorn. So here, the kernel of a matrix is very important related to that matrix. And therefore, as I said, important to study ax equals to 0, but notice ax equals to 0 has a very nice property, and this is actually a crucial observation that leads to the next chapter. Namely, if x and y solve ax equals to 0 and ay equals to 0, then, let's see, what about ax plus y? Ax plus ay, that's 0 plus 0, equals to 0. So x plus y also solves this. Solves, ax plus y equals to 0. Not only that, also, if c is a real number, then acx, well, that's c ax, and that's c times 0, and that's a 0 vector. So, cx also solves acx equals to 0. And by the way, this shows you exactly why, this and the previous theorem show you why they cannot be just exactly two solutions of ax equals to b, because of this property that if you have two solutions, you know, of ax equals to 0, you can also add them and get another solution. So you know, from this you can get infinitely many solutions of your equation. And however, the thing is, notice, so the crucial observation is that you have a certain structure. If you have two vectors satisfying the property, the sum of those vectors also satisfies the property. It's called closed under addition. And also, if a vector satisfies this property, any multiple of that vector also satisfies the property. And this is called closed under multiplication. So a huge, a huge chunk of time is devoted to study those structures, namely things called vector spaces, just with those two properties. That you know that if you have two things in that stuff, the sum of the things are in that stuff, and if you have one thing in that stuff, any multiple of that thing is also in that stuff. So the next deal is to study vector spaces. The nice thing is that just by studying those very abstract structures, we find that they're actually very similar to Rn. So it's a very technical definition, but basically you study vector spaces, and it turns out that, you know, those vector spaces are actually similar to Rn. If they're finite dimensional, they're isomorphic and to Rn. And there's a little bit of lingo associated to it. Let me just briefly mention it. So if you look at this example here, every x can be written as t times minus 2 times this vector plus s times 2 minus 1 this vector. We actually say that x is in the span. Okay. X is in the span of those two vectors, 1, 1, 0, 0, and 2, minus 1, 0, 2, 1. Not only that, but also notice those vectors, they're not multiple of each other's. So that's why we also call those linearly independent. Also linearly independent. So really, on the one hand, we have every solution to this equation is in the span of those two vectors. And those two vectors are linearly independent. What we really say, and again, that's more lingo, we say that minus 2, 1, 1, 0, 0, and 2, minus 1, 0, 2, 1 are a basis. For the space ax equals to 0. And that's really cool because basically what this says is that every vector, every solution of ax equals to 0 here can be just expressed in just one way in terms of those two vectors. In other words, if we just have info about those two vectors, we can get any x of this. And the reason this is, so nice is because this gives us a geometric interpretation. It tells us that the space of solutions, and remember that was our original goal in linear algebra, to study the space of solutions of this equation, is actually just a plane, sort of guided by those two vectors. So the solution, the space, of ax equals to 0 is a plane spanned, so a plane in R5, maybe guided or directed, I guess that's a good word, by those two vectors, minus 2, 1, 1, 0, 0, and 2, minus 1, 0, 2, 1. So literally, if you draw this, the space of these solutions, then it's just a plane, or let's say I'm magical and I draw R5, then the space of AX equals to 0 just looks like that. So where, we have those two vectors inside, minus 2, 1, 1, 0, 0, and 2, minus 1, 0, 2, 1. And not only that, from the previous theorem, we can also figure out AX equals to B. Well, it's either the point 0, it's either 1 point, no point, or just literally a translation of this plane. And in other words, we kind of answered our question, what do the solution of AX equals to B look like? Well, as I said, it's either the empty set, it's 1 point, or either plane or hyperplane or something three-dimensional or something higher dimensional. And that was like the big chunk, of the study of linear algebra is just more focused on studying the matrices. So maybe step 6. Given that matrices are so useful, is it sometimes possible to put it in a nice form? So can we sum our term 4, 0, 1, 2, 3, 2, 1, 0, 4. Let's say we have this really ugly matrix. Can we turn this into a much nicer matrix? 5, 0, 0, 0, 3, 0, 0, 0, 3. And again, it's nicer because it's diagonal. Everything is 0 except for the entries on the diagonal. And it turns out most of the time we can, and it's kind of related to a process called eigenvalues. It turns out, as I said, some are solutions to AX equals to lambda x play a crucial role in this process called diagonalization. But again, I won't go into the details of it right now. And of course, there's also a related thing. It's called the Jordan form, because even if you cannot turn it into a diagonal matrix, you can still most of the time, turn it into some matrix of almost diagonal form, let's say 5, 3, 3, where everything is 0, except possible the values here could be not 1, or the value here could be 1. So this is even in the case where you cannot diagonalize it, you can put it in what's called a Jordan form. And again, it's a lengthy process, but I won't go through this. And finally, maybe the coolest chapter of all, we actually talk more about geometry, and we talk about one process is called orthogonality. Namely, we talk about when two vectors are perpendicular to each other. Because whoever says geometry says parallel and perpendicular, so we can do that. Maybe the last step. Namely, one thing you can do, given two vectors x and y, you can define the dot product between x and y. And it's not the usual one, x1, y1 plus blah, 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 blah. But you can also define it more generally. And not only that, you can say that two vectors are perpendicular if and only if their dot product equals to 0. And since this is very easy to verify, it's also easy to verify that two vectors are perpendicular. And once you have that, you can actually define a very nice thing. It's called the orthogonal projection. Namely, suppose you have some space that you really like, and I give an example later, and you have a vector not in that space. It is possible to squish that vector on that space, but notice there are many ways of doing this. Like you can squish it this way, you can squish it this way, but those are not efficient. There's actually exactly one way of doing this that's very efficient in the sense that, x minus this vector is perpendicular to that space. And that thing is called x hat, and that's called the orthogonal projection. And is actually extremely useful when you have equations you cannot solve. Because what does it mean for ax to be equal to b, suppose, what does it mean for ax equals to b not to be solved? Has no solution. Surprisingly, it's still possible to find a solution of this, even though it has no solution. I know, creepy, but you can still do this. If ax equals to b has no solution, it means that this vector b is not in like the set of outputs of a of x. So space of outputs of a of x. It's called the column space, and it's just a set of all values of a of x whenever x is in Rn. Okay, and so because b is not in our desirable space, so again, a vector is in this space if and only if ax equals to that vector has a solution. Well, if b is outside of the space, one thing you can just do is just project this. Namely, define b hat to be the orthogonal projection, and by definition, ax equals to b hat has a solution. Ax equals to b hat, again, orthogonal projection, has a solution. Of course, it's not a classical solution of ax equals to b, but it is called the least square solution. It's like, it's the best non-solution. And it's super useful, in numerical analysis, in statistics, especially when you do regression, and in numerical, and other subjects. So least square solution. Especially in data science, because in data science you have too much data, yet you still want to figure out how an equation relating that data has a solution. Well, you can still do it using least squares. And last but not least, orthogonality is extremely useful in Fourier series. It's literally the basis of Fourier series. Namely, Fourier series is just a really cool way of expressing any functions in terms of trigonometric functions, like approximating, let's say, f of x equals to x with, sines and cosines. And that's it for the overview. As I said, I skipped many topics, but I hope that, I gave you at least a very nice intuition into the surface of linear algebra. Thank you very much.
And can I speak up for the viewers? Can we have Dr. Payan to do more videos on Fourier series for us in the future?
Yes, definitely. I love Fourier series.
Yay! Yeah. I'm pretty sure a lot of viewers will really, really appreciate that.
Awesome.
Cool. Yeah. Thank you so much, Dr. Payan.
Thank you.
Right now it's 6:30 p.m. All right?
On a Friday.
On a Friday,
which means I love you so much.
Yay! Yeah. So leave a comment down below for the support, for the love, right? Bye, everybody.
Bye.